I believe that there's one mechanism to rule them all. It's found everywhere in common objects, and today I'm going to show you how you can use it in your own designs to make them better. Designing and making your own mechanisms can be incredibly satisfying, but understandably, some people might find the process a little too complicated. So today the focus is on designing just one, the over-center mechanism. We'll look at real-world applications and then work through a series of designed examples so you can learn the critical characteristics. You might not realize it, but over-center mechanisms are all around us in everyday objects. The most common use you'll probably see are those satisfying snap-to-close latches that hold tool cases shut. But you'll also find over-center at the heart of more complicated mechanisms like vice grips. To break down exactly how an over-center mechanism works, I've created this very simple version. And like those toolbox latches, this is very satisfying to play with as it snaps into position. Let's examine the geometry. What you're seeing here is the simplest form of over-center mechanism that I could design. And like the real-world object, you can see that we can animate it and take it through its range of motion. Any of these mechanisms will have three main points that we pivot around, and the relationship between them is what's important here. For two of these points, the lengths will be the same through the full range of motion. For instance, the highlighted line between this top and bottom pivot point is always going to be 12 millimeters. And the distance between this top and side pivot point is always going to be 45 millimeters. But the distance between the final 2 points is going to be variable, and that is the key. We can see in this position it's a little bit over 44 millimeters. But as I start to lift it out of that position, it lengthens to 54. At the top it lengthens further to 57, and then as it comes over the other side, we can see it's getting shorter at 55. And then as we bring it down, it gets shorter still, ending up around 44 again. In real life, if we represent this length with a rubber band or a spring, we can see that as we lift the arm, the rubber band or spring is stretching, is at its highest tension at the top, and therefore if we let it fall at either side, it will want to contract and pull the arm down and lock it into position. And that's the crux of the over-center mechanism. In the middle of its range of motion, there's a lot of tension or resistance, and the mechanism wants to pull to either side. Despite the name, the mechanism never wants to rest over the center of the movement. In fact, resistance increases as we approach that center point, and that's what makes it so effective as a latch. It constantly wants to pull itself shut, and we can use these characteristics to our advantage to create very secure locking mechanisms. This is pretty satisfying to play with, and it would probably work well as a switch. But it's still quite simple, so now let's look at a more practical application. Let's move on to an actual locking clasp that you could use to hold two halves of something together. Let's have a look inside the CAD of this example, and once again we have 3 pivot points. The distance between these 2 upper points will always be the same. The distance between these 2 close points will also always be the same. But this third distance between the 2 furthest apart pivot points is once again going to vary as this arm swings around. In this lowered position, our latch should remain locked in place, because as soon as we straighten this, we reach the position of most tension, and that's our over-center point. But if we flip it up far enough, we'll lose tension, and the latch should come free and be able to swing out of this hook to open. We flesh out the design to make it 3D printable without support, and once it's assembled, we're ready to demonstrate. Keep in mind you would have the hook on a separate part, whereas here I have it all in one piece just to make it easier to display. We place the long position underneath the hook on the left, push down hard, and then it will lock into position, and then with a bit of upwards force we can go over center to unlock it and release the clasp. In our simple example, the arm that would vary in length was created using a rubber band which is designed to be elastic without breaking. Therefore, we could print it from any material we wanted as there was minimal stress on the plastic. This latch example, however, is made from all solid parts, no springs or rubber bands. Therefore, I printed it in PETG as well as PLA, and the PLA version does work, but it is quite a stiff material, and honestly, it feels like it's going to break if I use it too many times. Whereas the PETG version has a little bit more inherent flex, and this tiny bit of elasticity gives it a very tactile motion. If you're designing an over-center mechanism without rubber bands or springs, I recommend PETG. Another thing you can do to prevent your printed mechanism from breaking is to keep the distance between the two closest pivot points as short as possible. In its relaxed position, we're just under 45mm, but as we move it over center, we're just over 45mm. So that means the plastic component that goes between these two parts doesn't have to stretch very much. Now for fun, let's exaggerate this gap. We can see that at the bottom, we're just under 54, and over center, we're just over 55. So the more spread out we have these pivot points, the more this arm will have to stretch, and the more chance you have of breakage. But if this arm is represented by a spring or rubber band, you can safely ignore this consideration. Let's recreate another real-world example of a closing latch that wouldn't typically be called over center. In our example so far, as we've traveled over center, we've increased the length and therefore tension in the mechanism. But on this example, we instead have compression. We still have an over center point with a lot of pressure, but either side of that point, the latch is happy to snap into position. There's a couple of ways to achieve this, and the first version uses a cam, which is this raised lobe here, jutting out on an otherwise circular end. Like our other examples, we still have 3 points, so let's move the sketch and see how this operates. At the moment we're relaxed, but as we rotate up, we can see that the cam overlaps with one of the pivot points, adding compression. This position will have the greatest amount of pressure, but either side of that, the mechanism will want to snap to where it can move more freely. The trouble is, our plastic is solid, therefore I put a little cutout here, hoping it will flex inwards and stop the plastic from breaking. I molded up a quick base and then hit print. And here is the mechanism assembled. We can move freely, but as we push and approach the over center point where the cam is rubbing on the base, pressure builds up until we pass over center and it snaps into position, although it's still a little bit loose for my liking. That version was in PETG. I also tested this one in PLA, and once again it's much stiffer, so if your mechanism has a cam that adds compression, once again I wouldn't recommend PLA but rather PETG as it has more inherent flex. Here is a variation on this design. There are still 3 pivot points, but I wouldn't call this an over center mechanism. The distance between these two will always be the same, but thanks to the flex of the arm, these two will both vary a little bit. As we rotate the arm, we can see that once again, we'll have compression between these two pieces. Realistically, this elbow is going to flex to create a larger angle. Maximum pressure will be at the center point, but either side of that, the arm will want to snap to create clearance, whether that's opening upwards, or if we're closing the latch, snapping down to secure everything in place. So similar to an over center mechanism, just not quite the same. And here is our latest latch, printed in PETG and working perfectly. In fact, this one makes a satisfying clicking sound as it snaps into position. Because of the way this latch flexes, it feels like over center in that there's a high friction point in the middle and then it wants to slip either side. And because this flexing happens over a long distance, I found that PETG or PLA was perfectly suitable for this type of design. We have some functional designs, but let's finish with a proper project where the key element was an over center mechanism. This is a box of soda bulbs. They're actually carbon dioxide canisters, and I'm sure they're great for making soft drink, but I've never used them for that. Instead, I've used them for rocket propulsion, such as the sequence you see in the intro of my videos, but more significantly in F1 in Schools competition that we had a lot of success with when I was still teaching. To test the cars at school, you need your own track and launch system, but they are so expensive. So I did what many of you would do, and I designed my own from scratch, track and starting system. Originally, I made the mistake of thinking that the canisters were easy to burst and thought I would employ a solenoid to do just that. But it turned out that the membrane on the back is surprisingly tough, and any attempts to break it with something like a thumbtack will either break the thumbtack or maybe break your fingers. The solution turned out to be an over center mechanism, and a fair amount of people have contacted me over the years since making this video for my school. Sadly, I could never find the source CAD, but I eventually located it when preparing the video you're watching. The original was CNC machined from 12 and 3mm acrylic. This time around, I chose to laser cut a 3mm acrylic, in part so we can see the mechanism inside, and the rest I 3D printed, including some new custom parts to replace some of the weaknesses of the original design. If you did want to make your own one of these, I've uploaded all of the files and source CAD to printables, and I've got an unlisted step-by-step instruction video going through the assembly. For this video, however, we're going to concentrate on the over-center mechanism, and once again we can see that we have 3 pivot points. Like our simpler examples, the distance between these points follows the same rules. The distance between 2 is fixed, yet the distance where the spring is will vary as we wind back the mechanism. The over-center position is the position with the most resistance with these type of mechanisms, and from that center point it's desperate to snap closed to either side. And our simplest example from earlier is exactly the same. It wants to be anywhere except perfectly vertical over center. If we can balance the arm in that over center position, all we need to do is blow on it and that's enough to make it snap in the other direction. And that's how this launcher works. The tension builds and then the stopping point is just past over center. In this state there is a lot of stored energy and we only need the smallest touch from the solenoid to push it past the over center tipping point and to snap it down into the firing pin. Even just tapping the top with my hand is enough to trigger the mechanism, so a relatively weak solenoid can be used with this mechanism to impart quite a bit of force and burst the canister. I didn't have any dedicated CO2 cars handy, so I had to improvise getting a matchbox car and strapping with tape the canister on the roof. After an initial false start from the firing pin not being sharpened enough, attempt 2 gave the reliable operation that we used at school for many years, all thanks to an over-center mechanism. Let's quickly summarize for when you're designing. This mechanism has 3 pivot points, which we've seen in each of our examples. If we look at the straight lines between these pivot points, the length of 2 of them will always remain consistent no matter what the mechanism is doing. But the length of the third will be variable, changing as the mechanism moves through its range of motion. Peak resistance will be when all 3 points are aligned. When the pivot points are arranged in a straight line, this is what we call over center. And although we can balance the mechanism here, it's in an uneasy state because it has a desire to snap to either side of this over center point. And by understanding and manipulating this, we can create a clasp to lock things in place or release a lot of potential energy with a tiny push. Hopefully this video has demonstrated how versatile over-center mechanisms are, as well as the steps you need to design them. If you want to make or modify anything that you've seen in this video, all of the files and the source CAD are available for free on Printables. If you think another mechanism should be the GOAT, let me know what it is in the comment section below. Thank you so much for watching, and until next time, happy designing working 3D printed mechanisms. G'day, it's Michael again. If you liked the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.